Welcome to an exercise in reaction stoichiometry. Many times, what chemists need to do in the laboratory is to be able to determine how much of a particular reactant is required to produce a given amount of product. They also might want to know how much of another reactant is required to completely consume one of the reactants. So we use reaction stoichiometry to solve those kinds of problems, and I'm going to do several different versions for you that hopefully will help you learn this particular skill. Now, here's a question that we're going to deal with. How many atoms of hydrogen will be contained in the glucose that's produced from a reaction between 5.83 grams of carbon dioxide with an unlimited amount of water? So here's what this is saying. It is saying that we have 5.83 grams of carbon dioxide, and we've got an unlimited amount of water, so it rained. By the way, this is the photosynthesis reaction where plants take in carbon dioxide and water and they produce glucose and oxygen. In this photosynthetic reaction, we're going to figure out how many atoms of hydrogen would be produced if we reacted with a plant 5.83 grams of carbon dioxide and an unlimited amount of water. And of course, we've got the sun sitting up here because photosynthesis requires sunlight to energize this reaction. This reaction does not happen spontaneously without a source of energy, and photosynthesis uses the energy of the sun to do this. Now, in order to do any computation, reaction stoichiometry, you have to have a balanced chemical reaction. So let's go ahead and balance this chemical reaction. On the reactant side, I have 1 carbon, and on the product side, I have 6 carbons, so that seems like an easy fix to 6 carbons. Let's go ahead and do hydrogen next. You wouldn't want to do oxygen first. You would want to do oxygen last, always. I've got 2 hydrogens on the reactant side, 12 hydrogens on the product side, and so that again is an easy fix. 6 times 2 is 12 hydrogens. Next, we balance oxygen. I have 6 times 2, that's 12 oxygens on the reactant side, plus 6 more from the water. That's 18 oxygens total. Over here, I have 6 oxygens on the glucose, and if I multiply the O2 by 6, 6 times 2 is 12, plus 6, that's also 18 oxygen. So now I have all my atoms balanced. I've obeyed the law of conservation of mass, and that simply says that matter is neither created nor is it destroyed in a chemical reaction. The atoms just get rearranged, and this is the recipe for this particular reaction, so we've balanced our chemical reaction. The next thing that I need to do is I need to determine the molar mass of carbon dioxide. The reason for this is that I can't do the problem very efficiently going from grams of carbon dioxide to atoms of hydrogen. I just really don't have a way to do that very easily. The easiest way to do this problem is to convert grams of carbon dioxide into moles of carbon dioxide, and in order to do that, I need to determine the molar mass of carbon dioxide. Now, in order to determine the molar mass of carbon dioxide, I need a periodic table of the elements, and I see that carbon weighs 12.01 to 2 decimal places grams per mole, and oxygen is 15.999, which we're going to round off to 16. So now I can go ahead and I can compute the molar mass of carbon dioxide. I have 1 carbon, so that's 12.01 grams per mole, plus 2 times 16.00 grams per mole for oxygen, and that gives me a grand total of 44.01 grams per mole for carbon dioxide. All right, so now I've got the molar mass of carbon dioxide, and I'm ready to go. Now, I've given you a little simple strategy here, which we'll just go over real quickly. I can use the molar mass of CO2 and the reaction stoichiometry and Avogadro's number to convert grams of CO2 to moles of CO2, and then I'm going to use what we call the mole-to-mole ratio, CO2 to glucose, and there's more than one way to solve this, but I'm going to go from moles of glucose to moles of hydrogen atoms, and then to the number of atoms of hydrogen using Avogadro's number. So let's go ahead and set this up. I'll do it one way, and then I'll do it an additional way to make sure that you completely understand how to work this kind of problem. All right, so the most important thing to do is to start off right. And to start off right, you want the X factor. What is it I'm solving for? Well, I'm solving for X atoms of hydrogen. So X atoms of hydrogen. So if I get lost in my calculation anywhere, forgetting what I'm solving for, I can go back to the X factor and that'll tell me where to go. Now, I've been given 5.83 grams of CO2 to start with. The first thing I need to do is to convert grams to moles. In order to convert grams of any substance to moles of that substance, you divide by the molar mass. I'll say that again. In order to convert grams of a substance into moles of substance, you divide by the molar mass. So the molar mass of carbon dioxide is 44.01 grams per 1 mole. So that is going to cause grams to be canceled in our calculation. We're now in moles of CO2. I've converted grams to moles. The next thing that I want to do is I want to use the reaction stoichiometry, what we call the mole-to-mole ratio. And it's the mole-to-mole ratio, which is just the coefficient of the carbon dioxide to the coefficient of glucose. And if we don't have a coefficient there, it's understood that it's 1. So since this is carbon dioxide, it'll be 6 moles of CO2 to 1 mole of, and I'm just going to call this GLU for glucose. So now moles of CO2 have canceled and I'm in moles of glucose. Next conversion factor is to go from moles of glucose to moles of hydrogen. Now, this is an additional mole-to-mole ratio that we get just from the formula of the compound. So if I have just 1 mole of glucose, I've got a ratio of 12 hydrogens to 1 glucose. Now, it really doesn't matter whether I'm in molecules of glucose or moles of glucose. The ratio is still 12 to 1. If I have 1 molecule of glucose, I have 12 atoms of hydrogen. If I have 1 mole of glucose, I have 12 moles of hydrogen. So since I'm in moles of glucose, it makes sense to go from moles of glucose to moles of hydrogen. And we've just said that there are 12 moles of hydrogen in every 1 mole of glucose. That allows me to cancel moles of glucose. I'm now in moles of hydrogen. Now, finally, last step in this particular method, that was an ugly parenthesis, is to go from moles of hydrogen to how many hydrogen atoms there are in 1 mole of hydrogen, and that's Avogadro's number, 6.022 times 10 to the 23rd atoms of hydrogen in 1 mole of hydrogen. And that allows me to cancel moles of hydrogen. Now, to do this in your calculator, you just take 5.83 divided by 44.01, because there's no sense in multiplying by 1. So 5.83 divided by 44.01 divided by 6 moles times 12 divided by 1 times Avogadro's number. And when I do that, I get 1.60 times 10 to the 23rd atoms of hydrogen. So that's how many atoms of hydrogen are produced in a reaction of 5.83 grams of CO2 with an unlimited amount of water. You'll notice that I didn't need to worry about the water because there was nothing in the problem that requested the water. So it'll always only be 2 components that you're looking at. In this case, it was CO2 and glucose. So that's the problem. Now, I could have done this slightly differently. Mathematically, it would have made no difference. I could have gone from moles of glucose to number of molecules of glucose. So that would have put Avogadro's number right here. And then instead of doing what I did initially, I would have had 1 molecule of glucose going to 12 atoms of hydrogen. So all I would have done is transposed the 12 Avogadro's number, 6.022 times 10 to the 23rd, in the numerator. Mathematically, instead of multiplying by 12 times 6.022 times 10 to the 23rd, I would have been multiplying 6.022 times 10 to the 23rd times 12. So go ahead and try that out for yourself. Now, I just want to remind you that we were interested in finding atoms of hydrogen. That's the microscopic level, and what we started with was grams, and grams is definitely a macroscopic value. So is moles. So we were going from macro to the microscopic world of atoms and molecules, and when you do that, you have to multiply by Avogadro's number. And usually that's done somewhere toward the end of your calculation. In this particular case, what I'm going to suggest is that we go from atoms of hydrogen, we're just going to reverse this operation, to grams of CO2. So in this case, I want to find out grams of CO2, and I'm going to start out with 1.60 times 10 to the 23rd atoms of hydrogen. I've got exactly what we determined from the first one, so you can figure what the answer is going to be. And I want to know how many grams of carbon dioxide would be required to produce 1.60 times 10 to the 23rd atoms of hydrogen in glucose at the end of that reaction. So here we go. So this time I'm in micro world, and I want to go to macro world of grams and moles. So in that case, instead of multiplying by Avogadro's number at the end, I'm going to divide by Avogadro's number right up front. So 6.022 times 10 to the 23rd atoms of hydrogen equals 1 mole of hydrogen. That's my first conversion factor. And that allows me to cancel atoms of hydrogen. I've now left micro world and I'm in macro world. Now I want to convert moles of hydrogen to moles of glucose, and I have 12 moles of hydrogen in every 1 mole of glucose. Now, that's the mole-to-mole ratio that I didn't get from the balanced chemical reaction. I just got it from the chemical formula for glucose. It's a 12-to-1 ratio between hydrogen and glucose. And the next thing I want to do is I want to go from moles of glucose to moles of carbon dioxide. And for this, I do use the balanced chemical reaction to get the mole-to-mole ratio. And we see that 1 mole of glucose is produced from 6 moles of carbon dioxide. And so that'll be 6 moles of carbon dioxide. All right, so where are we now? We've got moles of hydrogen over moles of hydrogen, moles of glucose over moles of glucose. That gives us moles of carbon dioxide. And if I do one more calculation, I'm going to just, instead of dividing by the molar mass, I'm converting moles to grams. And if you want to convert moles of a compound, in this case CO2, to grams of CO2, you multiply by the molar mass. So I'm multiplying by 44.01, and I'll let you go ahead and calculate that in your calculator, and you'll get 5.03 grams of CO2. So just remember, if you're going from macro to micro, you multiply by Avogadro's number, and it's usually toward the end. If you're going from micro to macro, you divide by Avogadro's number, and it will be at the beginning of your calculation. So now we want to go ahead and we want to solve a different problem. Now this is really an easier problem to solve. Question: how many moles of glucose will be produced in the reaction between 3.8 times 10 to the minus 3 moles of water and an unlimited amount of CO2. So CO2 in this problem isn't a factor because we have all we need. So we don't need to worry about CO2. What we're looking for, though, is X moles of glucose. So I'll just call this GLU, and that we'll set next to an equal sign. On the other side is the other value that's given to us, which is the 3.8 times 10 to the minus 3 moles of H2O. And now what we want to do, and this is really a very simple problem. I don't have to worry about grams. I don't have to worry about molecules. So there's not going to be any molar masses. There's not going to be Avogadro's number. I'm simply going to use the mole-to-mole ratio between water and glucose. I'm not worried about anything else. And if I look at the mole-to-mole ratio of water to glucose that we saw earlier, 6 moles of water, H2O, are required to produce 1 mole of glucose. And that's it. The moles of water cancel and I have moles of glucose. So in my calculator, I'm going to put 3.8 times 10 to the minus 3 divided by 6, and that gives me 6.38. 6.38 times 10 to the minus 4 moles of glucose. Now that's a really simple problem, and people mess this problem up all the time. They overcomplicate it. If you're asked for mole and you're given moles, it's really a two-step calculation, just a one-step calculation really. X moles of glucose is equal to the moles of whatever your reactant is times the mole-to-mole ratio of what you're looking for. That'll be on top, and what you have in the balanced chemical reaction for a coefficient, that will be in the denominator. So this is just the mole-to-mole ratio, and that gets multiplied times what you have. Now we come to a more challenging problem. This is known as a gram-to-gram problem, or a gram-to-gram conversion. And the reason is we're going from grams of one compound to grams of another compound. We still need the balanced chemical reaction. We still need to convert grams to moles, but at the end, we're going to need to convert moles to grams. It looks like I didn't quite finish this. What is it that we're going to need the molar mass of? Well, it says how many grams of glucose. So the how many part is always the X factor. So that's how many grams, that's G, believe it or not, how many grams of glucose will be produced from the reaction of 7.57 grams of carbon dioxide. So what we need the molar mass of is we need the molar mass of glucose and we need the molar mass of CO2. Well, this one we already know is 44.01 grams per mole, but glucose, let's go ahead and let's figure out the molar mass of glucose. I'll do it down here. Glucose is C6H12O6. All right, so you go to your periodic table, and we're going to get the molar mass of this compound. So it's going to equal 6 times 12.01 grams per mole. That's carbon. That's the 6 carbons, plus the 12 hydrogens. I'm going to round hydrogen's molar mass to 1.01 grams per mole, and there's 12 of them, plus 6 oxygens, which are each 16 grams per mole. And when I calculate the molar mass, I get approximately 180.18 grams per mole for glucose. All right, so now I have the molar mass of glucose, I have the molar mass of carbon dioxide, and I have the mole-to-mole ratio from the balanced chemical reaction. We've actually already used that. So we're going to convert grams to mole. How do you convert grams to moles? You divide by the molar mass. 44.01 grams per mole. This is CO2. We've just converted grams of CO2 to moles of CO2. That grams cancels, now we're in moles. Now you have the mole to mole ratio, and the mole to mole ratio, we've already determined that from the balanced chemical reaction, is 6 moles. It's just the coefficient of CO2 in the balanced chemical reaction and the coefficient of glucose from the balanced chemical reaction. Last step, we've canceled the moles of CO2. We now have moles of glucose. Now we simply convert moles of glucose to grams of glucose. And since to convert grams to moles, you divide by the molar mass. Now we're converting moles to grams. You multiply by the molar mass of glucose. So in your calculator, moles cancel, and we have grams of glucose, which is what our X factor was. So we've set everything up correctly. Now all we have to do is plug it in the calculator, and that's 7.57 times 1 divided by 44.01 times 1 divided by 6 times 180.18 divided by 1. And of course you don't really need to plug in all those ones. And the result is 5.17 grams of glucose is produced when 7.57 grams of CO2 reacts with an unlimited amount of water. That's a gram to gram conversion. Now I want you to pay attention to something. Here we have 3 sig figs for the problem. We don't worry about sig figs in the mole to mole ratio or the molar masses. I ask you to please use at least 2 decimal places in your molar masses to give you an accurate answer. And since we have 3 sig figs for the CO2, we have 3 sig figs for our answer in grams of glucose. And that's it.